Excuse me. I will begin with a word of prayer. So, Heavenly Father, we thank you again for this day, and I thank you for this class, these students. Just ask you to, again, just give us wisdom, how to understand your creation, help us to understand a little bit more about linear algebra today, Lord. In your name I pray, Lord Jesus. Amen. So, I will post the solution for the quiz, and I'll just say that I don't think anyone really appreciated, and fair enough, you didn't have time, right? Granted. Problem 4. See, problem 4, you need to think more about problem 4. So I'm going to give you a chance to work on problem 4 for a few days, and so I'll collect it later again, all right? So problem 4 you can mull over, think about it some more. The point of problem 4 is, well, you should think about whether or not the given mapping is actually a function. Yeah? So this is a problem Dr. Sprano would like. It's I can't say much more without really giving you too big a hint. I just say, think about it. As I have that word there, discuss, that means that perhaps you need to supply additional information to make the problem meaningful, all right? And maybe you should explain what information lacking would make it not meaningful. That's the larger idea. So, and I think everybody here needs more work, or they should spend a little bit more time thinking about quotient spaces, because I think you guys are a little bit shaky on that topic, right? From at least what I remember in the grading. So just thought, yeah. So let's talk more about the Jordan form. So so we can either talk about the Jordan form of a linear transformation, or we can talk about the Jordan form of a matrix. And oh, thanks. So I probably should just make some definitions before we get further. So let's just define J sub k of lambda. What this is going to be is lambda times the k by k identity plus the nilpotent order k thing here, where nk is this, let's see here, it's got ones on the super diagonal. All right. So I guess you probably could come up with a formula for it in terms of the EIJ, you know, like if you wanted to. Like, what would this be? Let's try to do that. N sub k would be what? It would be E1, 2 plus E2, 3 plus dot, 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 plus, what's this last guy right here? That's in which row? The k minus 1th row and the kth column. So there's a, if you're not sure about what I mean by the plus dot 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 notation, that's an explicit formula for n sub k. The n is for nilpotent. Nilpotent means that there is a power to which if you raise the matrix to that power, you get 0. And this is a nilpotent degree k because the kth power is 0, but the k minus 1th it's not 0. So basically you can work on this. You can prove that n sub k to like the k minus 1 power, let me put some parentheses here, to the k minus 1 fold power, you just get E, like this one. So E, I guess in our current notation, EK1. All right, so this thing. Everything 0 except for that one solitary 1 down there. And then n sub k to the power k is equal to 0. So this makes this, n sub k is said to be nilpotent order or degree k. All right. So basically, this is K by K Jordan block with eigenvalue lambda, all right? And so to say a matrix is in Jordan form, what that means is that the matrix is formed by the direct sum, like a direct sum of Jordan blocks. So like, if A is equal to the direct sum, let's say I equals 1 to, I don't know, S of J K sub I lambda I, then A is in so-called Jordan form. So to expand this out, what that means is like you've got the first one, and then the second one. And by the way, folks, this is a matrix. Some of you were confusing the plus circle with the matrix and the subspace on the quiz. That needs to stop. These are very different. There shouldn't be a confusion between the direct sum of matrices and the direct sum of subspaces. These are radically different avenues of discussion. So anyway, there it is. This would be a Jordan form. And one thing to notice is, of course, what's like let's look at some special cases. So like J1 lambda, what's that? It's just a 1 by 1 matrix. This is what it means. And the 1 by 1 block is just solitary number 1 by 1 matrix. What's J2? We get lambda, like that. This is the 2 by 2 Jordan block. Why do 2 when you could do 3? J3 lambda, 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 and 2 1s on the superdiagonal. All right? Let's do more. J4. So I think at this point I'm just being stupid. I mean, I think you probably get the pattern by now. But just in case, here's what J4 would look like. This would be a good test question? See, if I ask this as a test question and you guys get it wrong, it's very depressing. If I at least ask a moderately difficult question, then you get it wrong, I can like solace myself. I gave them too much trouble. It was too much. There wasn't enough time. I can make all kinds of excuses for you, and I feel better about my life. But if I put this question on the test and you get it wrong, then that's like when I asked the intersection of the subspaces question on the final that other year. You know, that's a high stakes question, because if everybody gets it wrong, then I felt like I couldn't give an A. I don't want to be put in that position again. I can't ask easy questions. I have to ask harder questions. So, you know, anyway, I'll shut up. But here's some Jordan blocks. Now, what does it mean to say a linear transformation is, so like, if you have T from V to V, then T beta beta is in Jordan form, means that beta is a generalized eigenbasis. And I'd like to explore that more with you guys. Like I said, I'm not going to build the full theory of chapter 7. I'm going to try to illustrate more by examples in here on this topic. So let's get into some of these examples that I was claiming I'm going to give you. So first of all, let me try to explain what I mean by this. Yeah? What is it? Oh, you just wonder what I was up to? Okay.
Yeah.
Don't worry. I don't attack students from behind. I throw markers from the front.
I was worried that you were writing on a whiteboard in the back of the classroom.
And then you realized, But then you realize that there is no whiteboard in the back of the classroom, and then you feel better. No? I do write over there sometimes, though. That's true. Guilty as charged. Okay, so a generalized eigenbasis is basically, what this means is that the basis is formed by union of, like I talked about last time, k-chains. K-chains with various eigenvalues of T. So, and by the way, I call them k-chains, but I noticed that the book calls them a cycle. I think it was a p-cycle. I'll read it for you guys. The way the book presents it's slightly different. Which might be good to notice if I've assigned you homework problems from the book, which use that language. I just want to make you aware of it. If I can find it. So it's kind of like a question of, so the definition in the book is this, and it's a good definition, I suppose. Suppose T is a linear operator on V, a linear transformation on V, and X is in the generalized eigenspace with eigenvalue lambda, and then suppose P is the smallest integer such that T minus lambda to the power P acting on X is equal to 0. Then T minus lambda to the P minus 1 acting on X, T minus lambda to the P minus 2 acting on X, T minus lambda to the first power acting on X, comma X, is a cycle of generalized eigenvectors of length P. A cycle of generalized eigenvectors of length P, and they call this the initial vector. And they call this the final vector, I guess, if I remembered it right. Man, I hope I don't have those backwards. Let me check. That would be just like me. Like in differential equations today, I switched critical and, over and under damping. I feel like that's not the first time either that I've done that. So, my apologies. Where was I? Page 482 is where this definition lives. How to read that sentence? Respectively. I need to find someplace else where he's used the words to be sure. Tell you what, let's not fuss about this at the moment. I'm just going to erase those in the case I'm wrong. All right. I'll try to read the book and come to a specific answer, which I trust more, because I'm just anyway. So, like I talked about the chain conditions last time, right? And so for me, it's all in terms of more or less eigenvectors, right? So like I had, for me, the k-chain, they solve T minus lambda. So like I made V1 an eigenvector, right? And then I made V2 equal to that, right? So, and then remember this? And so forth and so on. And finally I get to T minus lambda to the VK minus 1 vk rather, equals to v, vk minus 1. And we proved that t minus lambda to the jth power acting on vj is equal to 0 in that setup. So you notice that in my way of thinking, I'm not emphasizing like, the way I look at the list of vectors is a little bit different, just in terms of the presentation of the definition. But the thing is, I don't think it's actually different. So here, if I call this thing v1, right? What's t minus lambda times v1? Think about it. It's what? It's t minus lambda to the what? Power p, acting on x, right? Which is assumed to be what?
0.
0. So see, this is in fact an eigenvector. And this right here, if I call this v2, it is true that t minus lambda times v2 is equal to what?
V1.
It's equal to v1, yeah. So their presentation of the chain, it's a little bit, again, they call it a p-cycle. It's a little bit different. So anyway, let me resist the urge to say further about this. I just want to show you examples today, so let me actually do that. All right. So I claimed that if your matrix is in Jordan form, then beta is a generalized eigenbasis. Let me explain how that works for a specific example. So example 1 here. Let's suppose A is like, you know, J2, 3, direct sum J4, 3, direct sum, oh, I don't know, J1, 7, direct sum J, let's go with 3, what eigenvalues, guys? What do you guys want? 24? Oh, okay, I'll accept it. It's almost 42. So I regret this example already, because now I'm going to write out A. What's it look like? I mean, you're like, you might say to me, isn't the point of this notation so that I don't have to write it out? Well, maybe that's true from one perspective, but I think if I don't write it out, it's not real to you, just given where you guys are in terms of abstraction and everything else, you know? So like, let's write it out. How big is this matrix? 10 by 10? All right. That feels like about this much space. All right. So I've got a 2 by 2 block here I got to fill in. I've got a 4 by 4 block here I've got to fill in. I've got a 1 by 1 block here I got to fill in. And then I've got a 3 by 3 block here I've got to fill in. Everything outside these blocks is 0. Right? So the J23 puts a what? We go 3, 3, 1, 0. This one, we do 3, 3, 3, 3, 1, 1, 1, everything else 0 in this block. 7. And 24, huh? So 24, 24, 24, 1, 1, 0, 0, 0, 0. I feel like I need some dividing lines. There it is. That's A. All right? So my claim to you was that if the matrix is in Jordan form, then, so if we're just talking, so if we were talking, if this was equal to T beta beta, right? I guess to go back to my comment, if this is equal to t beta beta for some basis beta, right? Apparently beta would be what? V1, V2, V3, all the way out to V10, right? If this is the matrix for t with respect to a choice of basis beta, what can you tell me? How are the V1, the V2, and all these things related? Like, what does this first column tell us? I mean, okay, so before I get over to here, let me just take a second and point out that if the matrix is in Jordan form, what that means is that the standard basis is a Jordan basis. Let me make that explicit here. So like, I'll repeat that again. The standard basis is a Jordan basis if the matrix is in Jordan form. So here I have AE1 equals to 3E1. I have AE2 is equal to 3E2 plus E1. I have AE3 is equal to 3E3. I have AE4 is equal to 3E4 plus E3. I have AE5 is equal to 3E5 plus E4. I have AE6 is equal to 3E6 plus E5. All of these things I'm writing down, I'm reading directly off the matrix because column 1, column 2, column 3, column 4, column 5, column 6, just reading off the columns, right? But what do these equations mean? So here we have a minus 3i E1 equals to 0, and we have a minus 3i E2 equals to E1. In other words, E1 and E2 is a 2-chain with eigenvalue 3. E1 and E2 is a 2-chain with eigenvalue 3. And if you sort through this, you get E3, E4, E5, E6 is 4-chain with eigenvalue 3. All right? Do you see that? Like this one, for instance, says a minus 3i times E4 is equal to E3. Do you see that? Right. Now 7, well, 7's just kind of a loner there, isn't it? You have a times E7. Wait a minute, is that the 7th spot? That would be perfect. 1, 2, 3, 4, 5, 6. Oh, it is the 7th spot. Wow, like I planned it. Not really. But here we have a E7 equals to, well, 7E7 as it happens. This makes, of course, a minus 7i E7 equals to 0. Again, you could you could look at E7 as an eigenvector from either equation's perspective, but I prefer to look at it equal to 0 because of the way the equal to 0 equation plays an important role in future calculations, you'll see. All right. So this is kind of boring. This one's just a it's just is a 1-chain. Okay. With lambda equals to 7, yay. And then this right here is going to make, if you don't mind me not going through the details, E8, E9, E10, a 3-chain with eigenvalue lambda equals to 24. All right? So that proves that the standard basis, E1 through E10, is a Jordan basis because it's formed by the union of chains. It's formed by the union of generalized eigenvectors for the matrix A. So for each chain we get one eigenvector. See that? One eigenvector for each chain. One eigenvector for each block. One eigenvector for this block, one eigenvector for that block, one eigenvector for this block, one eigenvector for that block. How many generalized eigenvectors of order 2 do we have for this thing? One for this block, one for that block, none here, one here. So there are 1, 2, 3 generalized eigenvectors of order 2 for eigenvalues 3. There's two generalized eigenvectors of order 3, just one of eigenvalue 24 rather. Generalized eigenvector of order 3, none for this one, one for here, and one down there. So there's two of those, generalized eigenvector of order 3. And there's only one generalized eigenvector of order 4 corresponding to the, let's see here, 1, 2, 3, 4, 5, E6. E6 is a generalized eigenvector of order 4, right? That's because you have the longest chain corresponding to the 4 by 4 block. So a k by k block corresponds to a k chain. And if the basis is a union of these k chains, it is a Jordan basis, which means that if you look at the matrix, you're going to have a Jordan form, right? Because if they satisfy the chain conditions, it means the matrix has this pattern. Does that make sense? I mean, I hope it makes sense. I don't think I've proved it in general, but well, maybe, I don't know. But so, yep.
So would this mean that any matrix that has just entries along the main diagonal, but nothing else except maybe ones at some points along the super diagonal could be in, but like even if it doesn't have the ones along the super diagonal, it could be in Jordan form if you just consider it to be the direct sum of a bunch of ones.
Oh, sure. Yeah, sure. So example, any diagonal matrix is in Jordan form. Any diagonal matrix is in Jordan form. All the blocks are 1 by 1 blocks. Every vector is an eigenvector. All the chains have length 1. What's interesting is that there's a theorem proved in chapter 7 that any matrix which has a characteristic polynomial which is split over your field has a Jordan form. So it's always possible to look at all the generalized eigenspaces corresponding to each eigenvalue, again, assuming you have enough eigenvalues, assuming we're not with that like rotation example in the plane that we looked at, right? Where we had eigenvalues which were complex, but we had a real map, right? As long as we're outside that context, if we have all our eigenvalues, if the characteristic polynomial splits into a product of linear factors repeated, each one of those repeated linear factors defines a generalized eigenspace, and we can always find enough chains of generalized eigenvectors that the span of those chains will fill out the eigenspace. So like k lambda, generally speaking, is going to be a span, and I think he uses like the notation, I think like gamma. This is a temporary notation for the sake of this conversation, okay? And so here I'm using each one of these like to denote a a chain with eigenvalue lambda. So that you can always find enough chains, right, such that the union of those chains forms a basis for the generalized eigenspace lambda. And there's a theorem in the book which says that if you have the so by the way, notice that this takes us also back to that T-cyclic discussion, because if you look at this, if I know, we talked about this last time a little bit, right? If I know the generalized eigenvector of highest weight, wait a minute, if I know the generalized eigenvector of highest weight, I can generate the rest of them with that, right? Like, for instance, here, if I was given, if you know E6, then like a minus 3i times E6 gives E5, and then a minus 3i squared gives E4, and a minus 3i cubed acting on E6 gives me E3. So if I have the top vector, I can generate the rest. And there's a theorem which says that if you have the top vector of each one of the chains, and if those top vectors are linearly independent, then the chains are linearly independent. And as such, you can form the basis like that. That's explained in chapter 7. But I'm not ready to prove it yet. My apologies. Yeah. Okay, so let's look at another example. Yeah. So by the way, so what's just to finish this example, T beta beta, what's the story there? It's all the same patterns, except what? Instead of E's, you got V's. Right? So like, for example, if I know, well, we've talked about this before, right? So if you have T minus lambda V equals to Vj equals to Vj minus 1, then correspondingly T minus lambda Vj beta equals to, the coordinate vector Vj minus J minus 1 beta, right? And this is vice versa. So like, this is, so I have, and this is, more specifically, this is the matrix of T minus lambda beta beta times the coordinate vector of Vj beta, right? So here's really the point. I should really put my arrow down here. So because this is the relation between the coordinate matrix and the relation for the linear operator, if I know these equations, so with this being A, right? And these being the standard basis equations over there, whatever equation I have for the standard basis likewise holds for the corresponding abstract basis. So like I can say, for instance, if I can say this without writing it, it would be helpful to me. So I'm going to say these things slowly. V1, V2 is a 2-chain with lambda equals to 3 for T. V3, V4, V5, V6 is a 4-chain with lambda equals to 3 for T. V7 is a 1-chain with eigenvalue 7 for T. V8, V9, V10 is a 3-chain with eigenvalue 24 for T. This is a basis for V, right? And I didn't even tell you what V was, right? It's an abstract vector space. It could be a set of polynomials, it could be a set of matrices, who knows, all right? In contrast, for the matrix A, the generalized eigenbasis is the standard basis. It's column vectors, all right? Okay. Let me do some more examples, if I can. Oh, thanks. Less talking, more exampling. So you guys might, giving you examples is easy. What would be much more laborious would be to try to describe the general algorithm for finding the Jordan form for a matrix. I don't think I've put that on you. I'm more likely to give you information about a matrix and have you interpret it in terms of the chain idea. That's kind of more where we are in this course at the moment. The actual problem of computing the Jordan form for an arbitrary matrix is a computationally challenging problem that really requires technology. Because you have to find the characteristic polynomial, and then you have to look at the different powers of like A minus lambda that appear. And you have to find like the kernel, of like the highest power of A minus lambda, and that gives you like a highest weight vector. You use that to generate a chain. Then you have to kind of keep that in mind, and then you look for another chain, right? But you got to be careful not to overlap with the chain that you already have. And there's a whole intersecting with what you already have process. It's a pain. So I don't think I put that in your homework, actually. You're welcome. My elbow. Example 2. Let's see here. What if we had the matrix of T with respect to beta is minus 3 and then 0, 0, 0, 2, 1, 0, 2, 0, 0, 0, 0, 2, 0, 0, 0. There we go. We'll just do a 4x4 example. So you guys tell me, what's this mean? So we'll let beta equal to v1, v2, v3, v4 for the sake of discussion. So you guys tell me, v1 is what? Fill in the blank. v2 is what? v3 is what? v4 is what?
Well, v1, v2, and v4 are eigenvectors.
Very good. v1 is eigenvector lambda equals to -3. Likewise for v2, right? But this time 2. And you said v4 as well?
Yes. Then v3 is a order 2 eigenvector.
Yeah. So yeah, so generalize eigenvector order 2 lambda equals to 2. And so if you put these two things together right here, we have v2, v3 is a 2 chain, right? With lambda equals to, that's all 2. 2, 2, 2, 2. Question, is this matrix diagonalizable? No. Is this transformation diagonalizable? No. All right. So there I'm relying on a bit of theory, which is that two matrices which are similar have the same Jordan form. Up to reordering of the bases. So like here's another example. Example 3. If we had, let's say, T gamma gamma equal to, I don't know, 2, 1, 0, 2, 2 minus 3, right? And gamma's W1, W2, W3, W4. Well, first of all, that's in Jordan form, right? And, excuse me. And also, you can see here that, let me just write it out symbolically here. So this is literally J2, 2, direct sum J1, 2, direct sum J1 minus 3, right? As compared to my previous example, which was J1 minus 3, direct sum J2, 2, direct sum J1, 2. These two matrices, I would say, have quote-unquote the same Jordan form. Up to the reordering of the blocks, this is what I'm talking about. They've got the same Jordan blocks, they're just possibly in a different order. There is a similarity transformation. It is possible to find a P such that like P inverse T beta beta times P is equal to T gamma gamma. All right, like you can achieve that. So, if you believe me, any matrix which has a split characteristic polynomial, it has a Jordan form. All right, so this is basically the theorem. If, the characteristic polynomial of A is equal to, product I equals 1 to S of, T minus lambda I to the m sub I, and Rats. I guess I owe you a minus one to the n power, because that's how we define the characteristic polynomial, so that the leading power had a power of, like the leading term had minus 1 to the n on it, because we took, is that right? Did we do determinant of a minus, how did we define the characteristic polynomial here? Do you guys remember?
Determinant of a minus si.
Oh, yep. So because of that, the variable, we get n-fold minus s's in the determinant equation, which produces this leading term of minus 1 to the n. All right. So here I'm assuming that a is m by a is fn by n, and that lambda 1 all the way out to lambda s are distinct. Well, I guess they don't have to be distinct. They don't have to be distinct, but they're elements of they're scalars in the field. All right. So that is to say that the characteristic polynomial splits. If that's the case, then you know, P inverse AP is equal to, you know, a direct sum of Jordan blocks. Forgot my notation. I equals 1 to S, let's say, of, you know, the k sub I of lambda I. It's a Jordan form, all right? That's the theorem. What can we do with it? One thing is, like I've been trying to tell you today, is if it is already in Jordan form, then we can easily write down chain conditions for the basis. And vice versa. If we're given chain conditions for a basis, we know that the matrix for the transformation is in Jordan form. What else can you do, though? What's the trace of a matrix? Oh, thanks. Like, what's the trace of A? I mean, it's the same as the trace of A times P inverse, PP inverse, right? It's a trip, which is the same as the trace of P inverse AP, which is the trace of this, you know, these things, right? What is on the diagonal of the Jordan form? All the lambdas, right? How do you take the trace? It's just what? It's the sum. It's literally the sum. You know, I equals rats. Let me be lazier here. Can I go back in time a bit? Man. I should have just like listed all of the eigenvalues as lambda 1, lambda 2, da, 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 all the way out to lambda n, allowing for repeats. Then I could write down the formula, just sum I equals 1 to n of lambda sub I. But as it stands, I have the annoyance of like counting how many copies of each, you know what I mean? Like, I guess I can do it. Right, so like, supposing these are, anyway, whether they're distinct or not, I'd get M1, I have M1 times, M1 times lambda 1, right? And then I've got M2 copies of lambda 2. In my current nomenclature, M sub s copies of lambda s. But really all that is the sum of the eigenvalues, right? I mean, it's M-fold. M2-fold there. m sub s fold here. So the trace is literally the sum of the eigenvalues. And what about determinant? How does the determinant of the Jordan form work? It's the product of the eigenvalues. Yeah. And we can see that explicitly from just calculating the Jordan form. All right. But there's much more to do with the Jordan form besides just this. So one of the major applications that we'll talk about, well, I got through 2 examples. I don't know, it takes well, three examples. But one of the major applications to the Jordan form is this. And I'll spend more time on this another day, but I'll just get us started on it today. This seems like a good thing to do now. If we're trying to solve the differential equation, dr dt equals to AR. So this is, here R is an n-fold n vector of unknown functions. I'll just tell you what happens. It turns out we can solve this problem completely with something called the matrix exponential. The matrix exponential, e to the ta, is defined by I plus ta plus 1/2 t squared a squared plus da 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 da. All right. I think this is a homework problem for you guys. If it isn't, it should be. But you can show that P inverse e to the ta times P is equal to e to the P inverse T times P inverse AP. Which means that you can take this and rewrite it as e to the T times the Jordan form of A. Let me just call that J sub A. I should have given this a name, the Jordan form of A. And the Jordan form of A is so simple that you can just straight away calculate the matrix exponential. I'll show you a simple example of this. If I have e to the, let's say, 3, 1, 0, 3t, I can look at that as e to the t times 3, 0, 0, 3 plus t times 0, 1, 0, 0. And if you work it out, this is actually e to the 3t times e to the t times 0, 1, 0, 0. But that is that n2 matrix. So this is e to the 3t times the identity plus t times n2 plus t squared over 2 times n2 squared plus dot dot dot. But the thing is, as we were talking about at the start of today, n2 is a nilpotent matrix of order 2, which means n2 squared is 0. So this is 0. And so the matrix exponential is simply equal to, you know, e to the 3t times the matrix 1, t, 0, 1. And if I wanted to solve the differential equation, x prime equals to, you know, 3x plus y and y prime equals to 3y, I can get solutions to it directly from that matrix. Like the solution is xy is equal to like c1 e to the 3t 0, 1 plus c2 e to the 3t t1. So anyway, this is just an example of some of the neat differential equation-y stuff we can do with the Jordan form. But it's so much more than that. Like the Jordan form allows you to take an arbitrary matrix and put it into a very, very simple form that you can prove things about. All kinds of general calculations are greatly aided by the Jordan form. Now, there's a great limitation in what we're doing at the moment, right? What's the fundamental weakness in our approach? What if the characteristic polynomial does not split? What do we do then, right? What do we do then? In that case, we're only going to work over the real numbers. and we'll see that there's something called a complexification, and we'll see how that goes. But like that's, I don't know if I start that next class. Maybe the class after next I start that. I have to look at my plan again. But anyway, that's it for today, guys.